This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Which gets us very nicely to our next topic here of
great
real-time hybrid simulation. This is one of the first times that we've done this at OSU. That's mostly been a Lehigh thing or other universities thing. But you did a real-time hybrid simulation right back here.
Well, I actually did it in the
other one.
flume. I did it in the other one, but we're going to do it here.
We're going to do it here. Yeah. We're not going to walk across the hall, as cool as that would be. But over there, behind the wall, we've got a 100-meter long wave flume. That's amazing. So can you talk about what real-time hybrid simulation is for people who don't know what it is, and why is that important, especially with what we just talked about, that fluid-structure interaction, that structure-soil interaction? There's a lot of reasons that is super important.
Yeah. Well, so traditionally we kind of divide ourselves up into two camps. We're either like the numerical person or we're the experimentalist. And so hybrid simulation tries to take the advantages of both. So if there's something that you understand enough to model it well, that can be housed in a numerical model. But if there's a portion of it maybe you don't really understand that well, then that can be physical. And so the entire idea of hybrid simulation is it hybridizes a physical and numerical sort of subsystem or subassembly, sometimes also called a substructure, and then combined, it represents the complete system. So you take a complete system, partition it into, let's say, two parts, a numerical part and a physical part, and then those things interact with sensors and actuators, and then the governing equations of motion or governing equations in general are then applied to that whole system. So in the case of fluid structure interaction, or at least with the few applications that I've looked at, we were looking at, say, modeling a monopile offshore wind turbine. And so we had a physical cylinder that was in our large wave flume. And then we were numerically representing the soil at the base. So that was numerical.
Because you can't get grains of sand small enough in scale to what you got.
You could, but that brings
practically.
Yeah. Well. So that's actually a very good point. But so we have the soil that was numerical, but we also had the wind that was numerical, and this is where the sort of scaling laws that you're bringing up are very important. And so if you have wind in the same setting as, say, waves, the typical similitude laws are really incompatible with one another. So with wind, typically you're using Reynolds scaling, and then with the waves or open channel flow, you're typically using Froude scaling.
Oh.
And so when you scale those two things together, they don't quite match. Like you're scaling different portions of the governing equation. And so with hybrid simulation, you can imagine like the numerical model is at full scale, and it's scaling up and down to sort of communicate with your physical model. And then you get around some of these similitude requirements.
So basically, kind of for people who aren't familiar with Reynolds and Freud and all that, it's like you have these two different kinds of equations that have different variables in them that some of them don't work at a smaller scale in the same way that the others do. So if you want, say, a 10th scale model of a wind turbine, you scale down the wind to 10th scale, it doesn't work the same way that waves do at 10th scale.
Yes. Yeah. So basically some of the forces equals 0 or equals mass times acceleration. So like some sort of variation on Newton's second law. And so that sum of the forces could be a whole bunch of different forces. So it could be the hydrodynamic forces plus the aerodynamic forces plus...
But the wind turbine doesn't care. It's just
whatever
force.
Yes. Yeah. And so, but those two forces will tend to scale differently as you go down from full scale to small scale. And so we were using hybrid simulation as a way of mitigating that. And this isn't really a new idea. So Norway's looked at a lot of hybrid simulation for floating offshore wind turbines. The idea of applying real-time hybrid simulation in this fluid structure interaction setting was actually an unfunded NSF proposal between like me and Jim Rickles at Lehigh and Dennis Israti at University of Nevada, Reno. So this is like, I'm not the only person that was thinking about this. This just I ended up being the person who happened to be here at OSU who managed to get it into the flume.
Yeah, which, I mean, all all of that shows the power of being part of a network like NHERI, where, I mean, Jim Rickles is at Lehigh.
Yes.
Guys can collaborate really closely and share your data on Design Safe super easily. So he's more than happy for you to get this award and use your data and help you get it the best you can, because it benefits him as well. And being part of the same network, we're all rowing the same boat in the same direction.
Yes, exactly.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation, grant number 2129782. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so that we can improve the show and also help others find our episodes in iTunes. Thanks for your feedback and support. We really appreciate it. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.